sequence of the hypothesis or proof. In this sequence is what is being proved by this proof. So symbolically, we can say that this hypothesis has this as its proves this thing. This argument proves this conclusion. So this symbol is a special symbol reserved for logical proofs. Now, clearly, if this is so, then of course this has to be logically a logical consequence of these, because each one of these steps are according to these principles. Is the if the converse was true, then you will be able to establish proof, logical consequence via a proof. So proofs will be adequate for the business of doing logic. So this whole question can be rephrased as, are proofs enough for logical consequence? If I give a proof, then yes, it's a logical consequence. But if it's a logical consequence, can it be proved? So I have to give you a list of these logical axioms and deduction rules. I'm going to flash them because I'm going to rapidly run out of time. To read this kind of formal logic, it takes some practice. People who are practicing mathematicians or students of mathematics are used to reading all this rapidly. Still, I don't have enough time for you to even read it rapidly. So I'm showing it all on one page just to make the point that there are not too many. A page full of logical axioms and deduction rules is all that it takes to make all possible logical arguments. So let's go on. Let's go on to this Gödel completeness theorem. And we saw that if something is a logical proof, then this is a logical consequence. And we asked whether logical proofs capture all logical consequences. And the answer is yes. This was proved by Gödel when he was about less than 25 years old, closer to 20 in fact, and he was a young graduate student. So because of this, we can say that this is a logical argument with this as the conclusion, if and only if this is a logical consequence of this. These two notions are the same. In particular, I could take an empty set here. Then I will simply say that if something is a logical truth, which means it's a logical consequence of the empty set of hypothesis, if and only if it can be logically proved from the axioms using the deduction rules. So therefore, the set of logical truths in a language is mechanically enumerable. Though it's not decidable, it is mechanically enumerable. We can program a computer to print a list of all of them. So this will go on and on. Because you can, because of those finitely many laws of producing proofs, you can one by one produce proofs of ever longer lengths and take the last sentence, which is therefore a logical truth, and list them one by one. This does not contradict the undecidability of logical truth, because there is no way of starting with a given sentence and telling whether it's a logical truth or not. Now, as you saw in all this, there's a very precise language, very precise grammar, and very precise rules of logical deduction, which give us logical proofs and truths. But not all truths are logical. Sorry, not all truths are logical truths. There are truths which are not logical truths. They are true, but not because of reasons of logic. So you need other hypotheses. And so, when you have these other hypotheses, how to incorporate that in our logical calculus? For that, there is a notion called a formal theory. And this theory should have the following features. There should be a first order language. Then there are the standard axioms of first order logic and the deduction rules. All this has nothing to do with the subject matter of your theory. But then there should be a set of axioms for the theories over and above the logical axioms. But these extra axioms should not be just anything. Whether something is an axiom or not should be mechanically checkable in a bounded number of steps. Otherwise, somebody shows you a proof and claims that something is an axiom and you have no way of verifying whether it's an axiom. So you should be able to verify it in a bounded manner. So this is what is a formal theory. And a model for the theory, so now it's not just now there are these extra axioms. So that should be an interpretation of the language in which each of the models. One is arithmetic, the other is set theory. In arithmetic, those axioms of the theory, the interpretation, for example, which makes the model true, has this as its domain of interpretation, 0, 1, 2, 3, blah, blah, blah. There can be other models as well. And then you interpret equal to 0, 1, successor, plus, multiplication in terms of this model. So in the case of arithmetic, let me display to you the axioms. The next 3 slides are going to be a bit mathematical, but then again the lecture will turn philosophical. So those who are not used to reading formal mathematics, please bear with me. So here are a set of axioms called Robinson axioms. And finally, here is something called the induction axiom schema. These are the axioms for arithmetic with which one can recreate a whole lot of arithmetic. There was a famous philosopher, Bertrand Russell, who seemed to believe, or who actually propagated the idea, that all truths of arithmetic are nothing but logical truths, and you don't need any extra logical axioms. And he tried to justify his philosophy by showing how all arithmetical truths are logical truths. He wrote 3 big volumes with his collaborator trying to prove it, but it all ended in failure and they could not do so. That's called Principia Mathematica. So ever since then, well, anyway, mathematicians always believed that mathematics needs axioms which are not just logical truths, but something specific to the subject matter of mathematics. I don't have time to go more into this, more in this direction, so let's go on. So now when we have such a formal language, to study it, we can once again deploy mathematics. So to study the formalization of arithmetic, we deploy arithmetic itself. As I told you, mathematics is the science of all structure and relationships. So to study the foundations of arithmetic, we use arithmetic. And so all things in your formal language are converted into arithmetic somehow. The rules of grammar, logical deduction, etc. become arithmetical relationships between numbers which represent those various sentences. So through all this device, one can translate certain important notions of purely into arithmetical sentences. One of them says that arithmetic is consistent. So another notion that one can translate is that arithmetic is complete, meaning every closed sentence is either a theorem or its negation is a theorem. And so with all this preparation, let me show my last very technical slide, and after that it's going to be less technical. So when we play this game of a formal language, logic, axioms, proofs, the hope is that we can set up a consistent formal theory of arithmetic so that every truth will become a theorem. We should be able to prove everything that is true, starting from these few axioms which are very obviously true. And this hope was totally dashed by the following theorem of Gödel in 1930. And in words, it says that if I have formal theory strong enough in which I can do basic arithmetic, and suppose the theory is consistent, then it cannot be complete. And so I cannot prove every truth as a theorem. Of course, I can have inconsistent theory. In an consistent theory, every damn thing is a theorem, but such a theory is no good. Now, one may say that, okay, if you discover something, some sentence which is true but not a theorem, you include it in your axioms, but then to this enlarged axiom system, again the Gödel theorem can apply, so there's no way out. So the lesson of this is truth cannot be captured by a theorem hood in any consistent theory which has a basic amount of arithmetic included in it. So you remember I said what is a domain in which logic works, and I said mathematics, of course, but even in mathematics there are limits to what logic can do. This is what this theorem tells us. Now, in the days when Gödel proved his theorem, Tarski had not yet come out with this simple definition of truth. So people were very suspicious about the notion of truth. They wanted to eliminate the word true from such theorems. And that's also possible. That is called a syntactic version of this theorem. It says the same thing in a different way. Now, Tarski began with the idea here and showed one more very fantastic thing. You see, among arithmetic sentences which refer to arithmetic, there are certain true ones and they have their numbers. So is there some arithmetical property of those numbers? If there is, then arithmetical truth will be definable wholly within arithmetic, definable. You won't have to say something is true. You'll have to say, take that sentence, take its roll number according to the following procedure. And if the roll number is prime, then the sentence is true. Of course, instead of roll number is prime, it may be some other complicated arithmetical property. But no, there is no way of replacing truth by any such arithmetical property is what Tarski's theorem says. Okay, so now the more technical part of this talk is over and I am going to look at the more philosophical aspects. Let's look at something very close to mathematics. Computer science is our sister science. And the ideas and discoveries of Hilbert, Gödel, Turing, von Neumann, Tarski, etc., who were the founding fathers of modern mathematical logic, became the foundation of modern computer science. And that's because, well, for more than one reason. One of the reasons you will think is that if you want to ask a computer to do something, for example, carry out a proof, or check a proof or whatever, then we need to completely understand what is a proof. Only then we will be able to program a computer to do the proof checking. So for this reason, you will expect that computer scientists need to study basics of logic, because only then a computer can carry out logical operations. Computer entirely depends on logical operations. Don't want more. One may think, yeah. So today, therefore, training in the form of advanced PhD level courses in logic is mostly confined to the computer science departments of universities, the kind of things and much more advanced things in formal logic and mathematical logic that, well, have been developed are not taught in mathematics department or philosophy department. They are taught in computer science departments. But of course, their focus is rather utilitarian and not very philosophical, I must say. But something in recent days has upturned this idea that you need to completely understand something if you want a computer to carry it out. That is machine learning. People have made the discovery over the last year or two. More and more people have become conscious of it, that unsupervised learning, where you don't try to transfer any of your basic wisdom to your computer, such unsupervised learning is far more effective than supervised learning, where you try to understand something and program a computer. So for example, the computer program which became world Go champion, beat the world, human world Go champion, was unsupervised machine learning. Okay, so much for computer science. Let's come to formal logic in physics. So application of formal logic to physics is not a direct process. You don't make a formal language in which the symbols refer to physical reality. Instead, it's a two-step process. First, the physicists make various mathematical models. So mathematical model in 2020 or even for the last 50 years, you will expect to be in terms of Bourbaki style mathematics. So for example, you may want to define a space-time to mean a pair consisting of a manifold and a semi-Riemannian metric with a particular signature. So physicist models are mathematical models. Once you have mathematical models, logical arguments within the model are carried out as standard mathematical arguments without direct reference to foundations of mathematics and formal logic. So then you just go on as in mathematics. Ideal. The philosophically more difficult part is the going back and forth between experimental evidence about physical reality and the mathematical models, and for which there is no key. So we talked about logic in computer science and physics. Now let's go on further. So when does it work? It works in these things, but when does first order logic work? So one has to say that there have to be robust individuals. X, Y, blah, 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 refer to individuals, or proper names refer to individuals. And these individuals have to be robust. If they're just waves in the sea and you say this wave and that wave, and within no time that wave has gone and some other has formed, so there are no robust individuals. So there have to be robust individuals. Then there have to be a few prescribed predicates, and you saw how few they were in the arithmetical example or a sectary example. And they have to be robust again. Something has a certain property, then as long as we are interested in this subject, it should have that property. Otherwise, you cannot go on talking about that. And everything that we want to say then can be said by the resulting sentences of a formal language. If you don't have such a formal language, then you can't expect logic to work. Then in this and, or, etc. should have their standard meanings for first order logic to work. As you know, this is not always the case. The Buddha is supposed to have said that something can be true, not true, and there are two other truth values, both true and not true, neither true nor not true, and then the standard meaning of negation is not going to apply. So standard logical meanings have to apply. If all this is satisfied, then we can trust the deductions made using logic from hypotheses which are true. Alternatively, you may have robust translation of the situation into clearly defined mathematical model as for physics. And then we can argue mathematically. That will be a logical argument. So these are the situations in which logic works. But the real world, where we must use natural languages and good mathematical models are hard to come by, are much more complicated. So let's enter now more and more into the real world. So let's look at natural language, some examples. These examples are not very complicated in some sense. You'll soon see very complicated examples, but they're already logically problematic. So look at this one. This sentence is false. You cannot formulate this sentence in one of our formal first order languages. But this sentence gives us great problems. Is it true? Is it false? Each implies the opposite. This is the liar paradox. So look at this. Is non-self-describing a non-self-describing phrase? Look at this one. Is the set of all sets which are not members of themselves a member of itself? This paradox does not occur in formal set theory. No way it can occur. And I'll tell you why later, if you ask me. Now look at something like this. Some girls in my college only talk among themselves. Now, here the word some is there, but the meaning of this some is not some individual, because an individual girl in my college only talks among themselves. What is that, among themselves? So this some girls clearly refers to a collection. So you need new entities like collections. Gangesh Upadhyay, the great Indian logician, realized this, that you need entities such as sets to make sense of various sentences. It becomes very complicated. Look at this. This is one of the paradoxes. The smallest natural number that's not definable using less than 20 words has just defined it in less than 20 words. Or think of a very modest man. Can he really say that he never talks about himself, but then he won't be modest anymore? So philosophers and logicians were naturally interested in all this, and they have made heroic attempts to understand this kind of things. I must say, not without too much success. The Indian tradition of this is called Navya Nyaya. I am not competent to tell you more about it, so you have to learn about it somewhere else. Okay, but now let's look at natural language in more everyday examples. These sentences are not everyday sentences that you're going to meet. So let's look at examples where the speech is everyday speech. So let's look at this. All shops around my house are closed on Sundays. Today is a Saturday, so they'll be closed tomorrow. Well, looks kind of logical. Therefore, I should finish my shopping today. Oh, really? So the first sentence looks okay. The second inference is quite problematic as it has hidden assumptions. After all, it may be the case that tomorrow I am going to go somewhere in another area where the shops are open. I am anyway going to go there and I might be able to do my shopping there. Therefore, it's not given that I should do my shopping today. So there are hidden assumptions. Look at this. Democracy is the best form of government. Therefore, support my revolution that will overthrow the king. Now, this is a very self-serving argument, and you're not going to call it a logical argument. And formal logic is going to be quite hopeless dealing with it. What's the definition of democracy? What's the definition of government? Is there some ordering on those so that something is the best form? What do you mean by the best form? Is there a uniqueness there? Then how does supporting my revolution help democracy? Aren't there some democratic countries which have kings? And so on, so on, so on. So there are too many ambiguous terms. So formal logic is helpless dealing with it. Now, there are arguments made by lawyers, as I told you right in the beginning. Lawyers make logical arguments, but now one can admit that they are called lawyer-like arguments. So let's not say more about them. So not unsurprisingly, formal logic, beyond some basic clarity in the use of expressions such as if, only if, and, or, not, for all, etc., is quite useless in most disciplines away from mathematics or computer science. Okay? Physics factors through mathematics. And how do you acquire competence in the use of if, only if, and, or, blah, blah, blah? That's, in my opinion, is best achieved through higher secondary education in mathematics. It's like instead of lessons in grammar, you learn the language, and then your grammar becomes okay. You don't have to learn too much mathematics to get your logic right. So let's come to language and the limitations of logic. This is my last slide. I have overshot by a couple of minutes, but then there were, okay. So, as we saw, natural language has unclear boundaries. But think about it, thought seems to exist beyond language. What we are interested more is thought rather than language, isn't it? And language is just a way of communicating thought, you may think. Yes, it does help think more precisely, but it's not the same as language. So think of infants, think of animals. Think you are playing table tennis. You don't have the time to say, oh, now he is going to place it there. Now let me give a top spin. Everything happens in split seconds. So think of music, not adequately linguistic. So all these do a lot of thinking, a lot of thought is involved here, but not linguistic thought. After all, our minds are products of evolution. Things have been going on for millions of years, and they are not formal systems. In the domain of precise language, truth, logic, and language is a middle domain in some sense of our experience in the world. And I always felt so, but I was very happy to discuss. In Bhagavad Avyakta nidhananyeva tatra ka paridevana. It means this: the origin of beings is inexpressible, the middle is expressible, and the end is again inexpressible. What is there to learn? Not continue their heroic attempts to push the domain language as much as they can, and not everybody turn into a mystic. But yeah, this seems very true. And so there is life before and beyond logic, and we necessarily go on as integral parts of the universe. Thank you.
Nice.
Hello.
Yeah,
so hello. Yes, thank you very much, Professor Nitsure, for very. Now there is some change. What we are going to do, I have put up the link now on the chat, and this link got Professor Abhyankar, so he wants to talk about Professor Abhyankar, and he will talk for about 13 minutes. That's the plan. So what we have done is, because he cannot enter for some reason which I don't know, because after 100 people try to join for the reason, and although some people have still he cannot. Therefore, we get a link, and that I have given, so people can start a new session. They can keep this session. There is no problem about it. They can start a new session on the given link, and they can listen to Professor Abhyankar. So there are no question answer session. Yes, please. Yes.
So you have given a link, Antri, where we can hear Professor Abhyankar?
On the chat. Link is on the chat.
On this.
Please go to chat.
Yeah.
Yes, there is a link. It is ending with ZN.
Yeah.
So you can.
Should I click?
You can start. This can be as it is. You don't have to go out of this. You can directly go to that one.
On this. Yeah.
Just I think click on that, you may go. I think that's. So then that new session will be there. In that he will speak. And then again we will come back to this session. People have already joined for this new session. Yes, people are coming. Yes. And people are requested to mute themselves so that the noise will become less. I was not sure it will work so nicely, but it is working. आता लोक तिकडे जायला व्हायला लागलेत. So I welcome all of you for this new session, and about 44 people have joined. We will wait for some more time, 2-3 minutes, and then I will be requesting Professor Abhyankar to speak on his brother, Sriram Abhyankar. And hello, Kashi. Yes, nice to see that you are here. Because it is an online thing, we could include you in the list of people who are attending it. Yes.
Hello, Katre.
Hello, yes. Yes, hello. So, Avanti, I request you to start it now.
Okay.
Yeah. Because some people may be joining, but it is okay.
Okay.
Yeah, because your next lecture also.
Hello.
People are requested to mute themselves.
Is this the correct link or we have to go to another one, sir?
Yeah, I have the same question.
I don't know because of what happened. I pressed or the other link, but I am here and I don't know.
Please join on other link. This meeting started.
Okay.
Which link is
Which one
this?
is that? Could you
Link
please
is posted in the chat box.
Okay.
But that's the one I used. FNB,
Yeah.
the one ending in FNB, no?
Z and Y.
That's
Sorry?
what I had done.
Please go to other link. Please go to other link which is there on the chat.
Can you
On
send
the
it
chat,
here
there is a
again?
link. New link I have given.
Okay. Thank you.
Please go to that one. Kulkarni sir, please go to the link I have given on the chat box. No, he is there. Okay.
Which one? The ZSP?
I have given the chat. I have given on the chat.
Okay.
Okay. Yeah. I have mentioned, and I think Tiwari also has mentioned that in his one again.
Okay.
Yeah, that one. Please, those who are in the current session, please go to the new session. New session is QXX TZTR ZNY. It is just you have to click on that link which I have given on the chat. Please go to chat. Avanti is presenting in the.
Okay. Yeah, it's not audible.
It's not audible. Yeah.
So I will click this one, huh?
New one. Yes.
So I click this and go there.
Yes. No, don't have to quit this. You can simultaneously go because host is different.
Oh, so lecture, I mean.
You can go to that one also simultaneously.
Okay.
You just go there.
Okay.
But one can quit and come back here if needed, I think.
Yeah. You can leave it and come back again. That is okay, but I am not sure whether you will be allowed. That's why I am not saying that you leave it. Okay.
Okay, sir, I want to speak here or that is link, sir.
Hello. Hello, Avanti. You have started, no? You can start. Hello, Avanti. Yes, you can start. Hello, Avanti. Yes, you can start.
Hello. Hello. Hello.
Hello, you can start. Yes. Hello, Avanti. Yes, you can start.
Hello. 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 Hello.
Hello, you can start. Yes. Hello, Avanti. Yes, you can start.
Hello. Hello.
हाँ आवाज ऐसा हे मिक्स्ड ऐसा you can start. Yes. Hello, Avanti. Yes, you can start. Continue करो.
Hello. Hello.
हाँ आवाज ऐसा हे मिक्स्ड ऐसा you can start. Yes. Hello, Avanti. Yes, you can start. Continue करो.
Hello. Hello.
हाँ आवाज ऐसा हे मिक्स्ड ऐसा you can start. Yes. Hello, Avanti. Yes, you can start. Continue करो.
Hello. Hello.
हाँ आवाज ऐसा हे मिक्स्ड ऐसा you can start. Yes. Hello, Avanti. Yes, you can start. Continue करो.
Hello. This one.
Okay. I think that this is over now. And somehow we could not hear actually, but we could see a number of pictures, nice pictures. So we thank and Yogendra sir and Sridhar Abhyankar sir for their presentation and the pictures especially that were shown in this. And now what we do is we leave for the original meeting. So we thank Abhyankar and their family again for this presentation and pictures. Thank you very much. Yeah. So please let us go to the meeting. Please leave this meeting and go to the original meeting. And then there we have lecture of Professor Raghava. So I am leaving this meeting now with thanks.
Yogendra here. Hello. Yogendra here.
Hi, Yogendra.
Hello.
Hello.
Yogendra here.
Yes.
Able to hear?
Yes.
Yeah. What I am saying that because of the audio problem, what we'll try to submit this completed tips sometime so everyone can later on watch. This was made by my daughter. She is great and somehow she is able to connect all of us here. So in order to have everyone watch this with sound, we'll try to send it later on. Everyone can have a look at it.
Okay. Okay, Yogendra. Katre should share the link, the original link.
Original link, you can type, yeah, that will be good, but people maybe they're in the old one also.
Please,
I'm typing it and just correct me. So I hope this is the correct link.
TZY DGNI FHB. That is it.
Sorry, Steve, I don't see it in that.
I typed it in the chat box.
Yeah,
Chat box.
but I don't see any.
You're talking about this chat box, but you are in the correct link already.
Let me just. I understand. There may be two different.
You don't need to do anything. Yeah. See, there were two links.
Yeah,
Also
created
some confusion for everybody. But okay, and in fact I see that I'm alive on both the links, so I'm going to quit the other one now and come back to this. So in other words,
if you don't see me there, you will have to call me, one of you. I have some difficulty.
One moment. Okay, let us see. Raghavan, are you here?
Sir, this is not the link.
This is not the link.
This is the third one. Which,
oh my God!
Yeah.
Why do you people create so many links? I don't. Okay. So is it the QBF?
TZY DGNI
Yes, this is the correct link.
Okay. Maybe,
Sir,
if
this is not
Raghavan,
the
if you are
correct
here,
link.
then this is
The correct link I'll share in this
Okay.
FHB. Yeah, ending with FHB.
FHB.
Yes. Yes. FHB.
Yeah.
Is the correct link?
Yes.
FHB I have sent, yeah, in
Okay,
the chat
so
box.
this QBF is
That
not the correct link. So we need to get out of here.
Yeah.
Okay, so let me quit. Raghavan,
Please. I just to check mistake. Is there anybody here?
Yeah.
Ending with FHB.
Is Raghavan here now?
Yes, he is there. Very much there.
Okay.
Yes, Sudhir, I'm here. Yeah.
Okay, good.
So we'll wait for some time. So I actually apologize for all this confusion, but it was a part of this whole game. And because Professor Abhyankar's brother, he could not join for some reason, which I am not understood completely. We had a way out that we should have another link and people are requested to join to that link and then again come back to original link. So all that great exercise all of us have done. So I thank all of you for that one. And now we wait for 2-3 minutes and then we'll start the next lecture. In the meantime,
Atre,
yes, please.
There was a question I was asked by someone else, and I think it was just showed up on chat also, that whether these lectures are getting recorded.
Yeah, we are trying to record it, yes. And I hope that will be done. It is being tried. And
yeah, you can record it, and after a while, it will automatically get dumped into some Google Drive folder of.
We can put it on YouTube. Actually, this is simultaneously being put on YouTube, but there was, because of this, I didn't get any support from our office staff, but I'm getting some support already in my house. So I'm trying to manage somehow.
Katwe, did you say that we are going to have? Katwe, did you say that we are going to have next section after 15 minutes?
Means 5 minutes, let us say. I mean, it is actually due 4:15. This in between, we are having this lecture and this whole thing. So 5 minutes is something which we can allow. And after this lecture, there is 15 minutes gap we are having. Yes.
What's the word? Where is the chat? The chat.
So now it's a free time, huh?
I mean, it is 5 minutes free time, you can say, if you like. Now, 5. So, we can start due time. But
not very, but okay. Arwan is there, so I was thinking.
Hello, SMS.
Yeah, wait, let me. He said.
Yeah, he said, but you are on your then
Yeah, Goipade.
Hi.
Hi. How are you?
I'm good.
Yeah. Is Amatto awake?
You should know that, no?
No, I don't know. I mean, we are in the same city. And how about Ravi now? Ravi, how are you? Here is the speaker. No? You look different now, Goipade.
Do I look different?
You look different now. I was seeing different too.
Everybody.
Hi, Raghavan.
Hello, SMS.
Yeah. So.
By the way,
shall we now-
said Amartya is awake.
Amartya, yeah, I can see his eye open. Yeah.
So probably shall we start the second? I think
Yeah.
Okay, we can start so that.
I'll
So now we are starting the second lecture. So the first lecture was with Professor Nitsure, who just mentioned that Professor Nitsure is associated to Bhaskaracharya Pratishthan for many years, and he is a trustee and governing body member of Bhaskaracharya Pratishthan, and he helped the Pratishthan in many ways. And I remember when as Abhyankar used to be in Pune, he used to discuss many things with Abhyankar. There will be chatting and fighting, everything he used to go in the usual way. So anyway, we thank Professor Nitsure, and now we invite Professor K. N. Raghavan from Institute of Mathematical Sciences. And he mentioned to me that when Professor Abhyankar was in Purdue, he was also in Purdue as a PhD student, and then he had good association with Professor Abhyankar. And we are very happy that Professor Raghavan is here today to give his lecture. So now we request him to start.
Okay, I'll start presenting now.
Yeah, please just start presenting. Yeah.
Yeah, can all of you see this?
Yes, we are viewing it. Yes, yes, we are viewing it. Yes.
Let me go to presentation mode. Is this clear enough?
I mean, it is clear, but do try presentation mode. It might make it.
It's not going to presentation mode. I'm trying it.
Maybe stop sharing, make it full screen, and then start sharing again.
Okay, I will do that. We'll do that. Yeah, just one second. I stop sharing.
So it is visible.
It's visible, but it's not in presentation mode. So let me try presentation mode. This will just take 1 minute, please. Bear with me. Okay. Okay, let's see if it works. No, it doesn't seem to work, Raghuram. So it's back to non-presentation.
Yeah,
I don't know.
Yeah. I mean, this is clear enough. You can.
This is clear enough. Yeah, thanks. Okay, and so let me begin. I thank this. I'm very much honored by this invitation, and I thank Bhaskaracharya Pratishthan and Professor Katre for this. Indeed, as he was saying, Abhyankar was a distinguished professor at Purdue at the time I was a graduate student, and among many meetings that I had with him at that time, I remember one distinctly, which happened over a winter afternoon in Sudhir Ghorpade's house. Sudhir had a married student housing quarters, and to which Abhyankar had come over, and several of us spent from morning till I think late in the night. I mean, maybe even past midnight. And he was holding a court, and it was a very nice learning experience for me. So let me begin my talk. You see the title and some, as you can see, it is joint work with Mrigal Singh Kushwaha, who's a PhD student at the Institute of Mathematical Sciences, where I work, and Shankaran Vishwanath, who's a colleague. And I've given you a reference. And the title of the paper has nothing to do, as you see, with the title of the talk itself. That is a comment on the way mathematics is written and communicated. for me, I think about very simple things, symmetric functions. But when we end up writing it for an audience, then it gets so incomprehensible, and you see there's the title. Of course, it is much more generalized, and what we are going to talk about today is just a small shadow of the actual thing. But I don't know if it's such a small shadow, because the shadow does capture, and I at least think in terms of the shadow most of the time. Okay, so a few more comments before I actually begin the talk. Despite the technical terms that you see on the screen, I intend this talk to be very understandable by even a BSc student of mathematics. In fact, as Abhyankar may have, school algebra is all that you need. Maybe you need a bit of college algebra too. Yeah, mostly high school algebra, a bit of college algebra is good to understand this talk. And up with what Nitin said, there is a road leading up and a road leading down, he said, and he took the road that was leading down. This seems like I am going to take road leading up, but I'm not doing that. I am what we are going to do is on flat ground, but we will stare up. That is the kind of so I try to give you a glimpse of some modern contemporary research, but never leaving the world of high school algebra or college algebra. In other words, rarely do we have the opportunity to connect what we are doing with something very simple. But I am in that happy situation where some recent research work is actually, I can communicate and connect with something very simple, namely symmetric polynomials in 3 variables, say. And I want to exploit that. And so I repeat, we will take we will walk on flat ground, so to speak. Therefore, we will never leave the realm of high school algebra or college algebra, but we will be staring up and not down. Okay, so there is no logical, the logic that is involved is something that we are all familiar. We are just doing mathematics. Okay, so one more slide of some high address students. You can, this is just to give you the terms that we are using. This is only to show how they are logically related to algebra. Okay, this is the executive of the talk. Symmetric polynomials. I'm going to be talking about symmetric polynomials. For a minute, okay, I must have used the word symmetric functions on the first slide, and I'm saying now symmetric polynomials. When I say symmetric functions, I mean symmetric polynomials. So even if I say functions, I'm only talking about polynomials. Okay, symmetric polynomials are interesting, not just for their own sake. So you could be interested in them for their own sake. You may think that they're interesting, in which case it's very good. But if you are going to say, okay, why should I be interested in this? What does it, what are they good for? Then here is the answer. They appear naturally in various contexts: physical contexts, mathematical contexts, geometrical contexts. For example, in geometry, in the study of cohomology of Grassmannians and other homogeneous spaces. So if you don't know these words, it doesn't matter. We are just saying that they occur in other contexts, that's all. In the representation theory of semi-simple Lie algebras, such as the special linear Lie algebra, SLNC, which is just n by n matrices with complex entries and with trace 0. Okay, I put this in brown font, brown color, because you need not understand what those terms mean. It is just to say that they appear in various contexts. Now, consider the space lambda n of symmetric polynomials in n variables over C. So we have n variables, let's say 3 variables, 1, 2, 3, or x, y, z. x1, x2, x3, or let's call them x, y, z. And I look at the space of all symmetric polynomials. When I say space, I mean the vector space, because you can multiply, there is a natural complex vector space action. We'll talk about this in more detail. It has many different vector space bases. Perhaps we will talk about one particular basis to begin with, but that's not so interesting. The more interesting basis is the one of Schur polynomials, which we will talk about later in the talk. And the question is really this: since Schur polynomials form a basis, I can take two Schur polynomials and multiply them, and they are symmetric. So when I multiply two symmetric polynomials, I get another symmetric polynomial. So I can express that symmetric polynomial, the product of these two Schur polynomials, in terms of the basis of Schur polynomials. So I get some constants in front of the coefficients. These coefficients are calculated by what is technically called the Littlewood-Richardson rule. It has geometric and representation theoretic significance. Now, what we will do in the talk is the following. I will talk about symmetric polynomials. We'll start from very basic high school algebra. Anyway, I'll do this explanation in terms of this outline here. We'll talk about what are symmetric polynomials. We'll talk about elementary symmetric polynomials, how to parameterize the set of symmetric polynomials, rather parameterizing set for a basis of symmetric polynomials. And then I'll define the Schur polynomials, and that is one of the important aspects of this talk. We will give two different definitions of Schur polynomials, and the definitions themselves are mathematically very interesting, and that is one of the take-homes from this talk that students should look forward to. And then we will come to the Littlewood-Richardson rule. This is a complicated rule, so I will not give you the general rule. Rather, I will just illustrate it in a simple case, and that will give you a flavor. It is the idea that is important, the thought that is important. The actual rule is combinatorially quite involved, and we will not get into it in great detail. But I hope I hope you will get the flavor of the rule. And then I will briefly talk about the recent research work that was hinted at on the first page, the title page, and I'll end with some concluding remarks. Okay, so we now begin the talk. Okay, so are there any questions? Is the pace okay? I hope I'm not going too fast. Like Nitin was saying, or I heard yesterday I was at a talk where a very distinguished speaker was saying he's not used to giving online talks because there is absolutely no feedback. So I'm facing the same problem here. So I don't know how this is going.
Just fine, Raghavan.
Okay.
I am at least understanding this.
Okay. Okay. Thanks. Thanks, Raghuram. I hope this is okay, Professor Katre.
Yeah. Please go ahead. Thank you.
Okay. Let's go back to do some high school algebra. Okay. So I've given you a polynomial here, x1 cubed plus 2x1 square x2 plus 2x1 x2 square plus 2x2 cubed minus 7x1 x2, and in two variables, x1, x2. Of course, the reason I say in two variables is that you can think of this as a polynomial in three variables or four variables where the third and fourth variable do not appear. That is possible, but so it is important that I tell you what the variables are, x1, x2. So the question is it symmetric in x1 and x2? So of course, rather than giving you the definition of what it means to be symmetric, I'm doing this by means of examples. So symmetric means when I switch any two variables, here of course there are only two variables, when I switch x1 and x2, substitute for x2 for x1 and x1 for x2, I must get back the same polynomial. So if we do this, the first term will become x2 cubed, but then that is here. The second term will become 2x2 square x2, which is the third term. And the third term will become 2x2 x1 square, which is the second term. The fourth term will become the first term, and 7x1 x2 remains. Of course, it becomes 7x2 x1, but that's the same as x1 x2. We are thinking of commuting polynomial. The variables do commute by our assumption. That's part of our assumption. Therefore, as we do in high school, therefore this is a symmetric polynomial. Is this clear? Okay, let's look at another example. How about this one? I want somebody from the audience to answer this question, preferably a student.
There is an answer in the chat box.
Okay. I'm not able to. Maybe Raghuram, you can read it out to me.
Yeah, so Manisha Garg says, yes, it is symmetric.
Well, let's see. Suppose I switch x1 and x2. Then
Jadhav just said it's not symmetric. So,
okay, so there is, okay. There are two kinds of opinions then. It is and it is not, right? And we are in the we are in a logical world, so both cannot be true. Unlike the example of Buddha that we saw in the previous talk. So either it is symmetric or it is not symmetric, right? So both cannot be true. So let's see. It looks, it has some kind of symmetry because it has a kind of this x1, x2, x3, this minus x1, minus x2, minus x3 is no problem because if I switch, then no matter which two variables I switch, this part gets me back the same thing. However, if I look at the third degree term there, it has a cyclic symmetry. When I move x1 to x2 and x2 to x3 and x3 to x1, it is symmetric. So when I cyclically permute the variables, seems to be symmetric. But if I switch x1 and x2, then I get this term becomes x3, last term, for example, becomes x3 square x2. I'm doing nothing to x3. I'm only switching x1 and x2. So x1 becomes 7x cubed, 7x3 square x2. And that term is not there in this polynomial. So this is not symmetric. Okay. And how about the third one? I can't see the chat box, so can somebody please read out the chat box to me?
There is nothing more in the chat box. So
sorry.
Okay. About the third one. I don't know.
Okay, so I hope you agree with me that the third one is symmetric.
Yeah. Okay. Now several people have said symmetric. So it's just
symmetric. Okay.
Yeah,
Okay. So let's summarize that. Okay. So I hope it is clear. I have not given you a formal definition. I have not written down a formal definition. I have said it in words. So a polynomial in some number of variables. So you should specify the number of variables. Again, if I think of this, if I think of, say, the third polynomial in 4 variables with another variable x4, then it's not going to be symmetric because if I switch x1 and x4, then I'm able to switching x1 with x4 is a possibility. And if I do that, then there will be terms involving x4, which are not there in this polynomial, right? So when I say a polynomial is symmetric, I have to say symmetric in which variables are you talking about, okay? So, so I hope this slide is clear now. The first one is symmetric in the 2 variables x1 and x2. The second one is not symmetric in these 3 variables. For the reason x2, I don't get back the same polynomial. And the third one is symmetric because no matter which 2 I switch, then I get the same polynomial. Now, as you may know, let's do some college algebra now. We just did some high school algebra. We'll do a little more high school algebra in the next few slides, but let's do some college algebra. So, so the symmetry group is generated by these transpositions. What that means is, I can do, once a polynomial is symmetric in this sense, that in the sense that if I switch any 2 variables, then I get back the same polynomial. then it also follows that if I permute the variables, substitute, instead of x1, for example, do a cyclic substitution, like x2 for x1, x3 for x2, x1 for x3. If I make that change of variables, then the polynomial again will not change, and so on. That is because the symmetric group is, and what that means, is generated by the transpositions. Okay, now let's do, here is another high school problem. Okay, if x1 and x2 are the root of the polynomial t square plus, okay, 2019 t minus 5, you can see that some slides for this talk were from the previous year. That's why I've used 2019. If I prepared it today, I would put 2020 there. What is x1 square plus x2 square, right? So how do we do this? Well, if you just recall your 8th standard or 9th standard mathematics, then you will say x1 plus x1 square plus x2 square, you will be able to write as x1 plus x2 whole square minus 2x1 x2. And x1 plus x2 is the sum of the roots, which you can read off from the coefficient. x1, x2 is also, you can read off from the coefficients of the given polynomial. And therefore, you are able to write x1 square plus x2 square. Okay, there it is, right? So I've given you the solution. This is a very simple high school solution. But the point is the following. So suppose I ask you a question like, if x1 and x2 are roots of the polynomial t square, the given polynomial, what is x1 square plus x2? Suppose I ask that question. That sounds like a, in fact, that is not even a well-posed question, because what is x1 and what is x2, right? So the x1 is one root and x2 is the other root. We are not telling x1 is this root and x2 is the other, we are not telling which root is x1 and which root is x2. So in posing such a question, it is important that when I say what is this polynomial x1 square plus x2 square, and so that polynomial that I ask you to compute its value, whose value I'm asking you to compute, must be a symmetric polynomial. Only then does it make sense, right? So what we are using here, without what we used in 8th standard and 9th standard, the intuitive understanding of the following fact, that if I am given a symmetric polynomial in two variables, then I can express it as a polynomial in x1 plus x2 and x1 x2. And x1 plus x2 is one of these coefficients, and x1 x2 is the other coefficient with some negative signs, appropriately done. And so I'm able to compute any, that is what we never perhaps stated it in so many words in high school, but we intuitively understood that. Okay, let's do one more high school problem. Okay, the reason why this is there is in the first one, I sometimes get the answer for this. So let me go back to the question. So some people answer this as, oh, I can use the quadratic equation and write what x1 is and what x2 is. The solution of the, as Abhyankar was fond of saying, Sridhar Acharya's method, right? So minus completing the square, minus b plus or minus square root of b square minus 4ac by 2a, that famous formula that we have. You can use that formula. You can write out what x1 and x2 is. Maybe you have them switched, but it doesn't matter. And then you can do this, but that's not a smart way of doing it, because if you use such a method, then this will be hard to do, because you have no such formula available. This is a degree 5 equation. But nevertheless, a question like this you can still answer, because again, this is a symmetric polynomial in the roots, and therefore you can write this in terms of the sum of the roots and other what are called elementary symmetric polynomials. Let me go. So these are the elementary symmetric polynomials are the coefficients of this equation here, t minus x1, t minus x2, t minus x3, t minus x4, and t minus x5. If you expand it here, right? And so here, so there is the answer, because then this is the product of roots taken 2 at a time, and that I can read off. That is this polynomial, this coefficient here of t cubed. And once again, I have this symmetric polynomial expressed in terms of the sum and product taken 2 at a time, and I have this answer. Okay, so formally here is the definition of the elementary symmetric. Again, I've said here functions, but you can functions means polynomials for me in this talk. So this is the definition of elementary symmetric polynomials. They are the coefficients of the equation t minus x1, t minus x2 dot 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 t minus xn. Okay, and now okay, I've said this here, right? These appear as coefficients in this polynomial, as we understand from high school. And here is the theorem. Any symmetric function in n variables, x1 through xn, is uniquely a polynomial in the elementary symmetric polynomial c1 through en. So the existence that it is expressible as a polynomial in the elementary symmetric polynomials we've used in the previous slides. But what we are not told in high school, and perhaps we don't pause to ask that question, is that it is uniquely written. So for example, this thing that x1 square plus x2 square we wrote as x1 plus x2 whole square minus 2 times x1 x2. That is the only way you can write it as in terms of x1 plus x2 and x1 x2. There is no other expression for x1 square plus x2 square in terms of x1 plus x2 and x1 x2. That is what this uniquely refers to. Okay, what that means for us is the following. Another way of saying this is the following. So now I'm doing some college algebra. I'm taking this ring now, polynomial ring with coefficients in the complex numbers. It doesn't matter. You can work with real coefficients. You can even work with integer coefficients. But since very soon I'm going to talk about linear combinations, and people may be more comfortable using a field rather than integers with the word like linear combination. So I've chosen to use a field. Okay. So this is C of x1, x2, xn is the ring of polynomials in n variables. Okay. And within that is this subring, which is generated by E1 through En. So these are all polynomials that can be written in terms of the elementary symmetric polynomials. But this theorem says that precisely that is our, so this lambda n is my notation for the symmetric polynomials, the space of symmetric polynomials in n variables. Now, one thing I will take it as obvious is the following, that this lambda is a subring in the sense that if I add two of these polynomials, if I take a linear combination of them, if I multiply it by a scalar, or if I multiply two of them, I get another symmetric polynomial. Now this is very easy to see. This is because whether you do the operation before you do your exchange or after you do your exchange, it doesn't matter. Anyway, that's an elementary thing that you can easily convince yourself of. Okay, and so we have this. This is just the expression of the previous theorem, except that we also have this additional information that this, you can think of this C, E1, E through En as itself a polynomial ring, because there are no relations among the E1 through En. That's what it means to say that it is uniquely representable as a polynomial. Okay, so we have, if you want, one copy of the polynomial ring sitting inside this polynomial ring. So this, the copy that is sitting inside is where you think of E1, E2, En themselves as variables. You can do that because there are no relations among them. Okay. Okay, that's what I have said here. The ring of symmetric functions is itself isomorphic to a polynomial ring in n variables. Now, let us look at the conclusion from this. Okay. Now, if mill ring, let's take this C x1 to x1, x2, xn. Then, what is the basis for this? What is the basis over C? This is a complex vector space. What is the basis over C for this? Well, very natural and the simplest basis one can think of is the basis of monomials. I take all monomials in x1, x2, xn, and they will be a basis for, after all, that's what we mean by a polynomial. It has monomials and then some coefficients in front, right? And we sum. So it's sums of monomials with complex coefficients. So by the same logic, we have now a basis for the vector space of symmetric polynomials. Now, what is that basis? It consists of monomials in these variables E1 through En. So, what this has gotten us for us, this theorem, which we know from high school, at least part of it, tells us that a basis for the symmetric polynomials consists of monomials in the elementary symmetric polynomials. Okay, so but there is one issue with this, and that we need to address, and the next few slides.
Is this theorem really a high school theorem? Did you say?
Yes, it is. If not a high school theorem, it is really a college theorem. It's quite. I am not proving this theorem.
Is it not Kolmogorov's theorem?
I don't know. It must have been. I don't think it is that recent. It is definitely. I'm sure it was well known to Newton, perhaps.
Or Newton. Sorry, Newton. Yeah.
Newton.
Or maybe even earlier. I don't know, but definitely perhaps Newton. Yeah.
Newton, yes, I mean.
Yeah. In any case, it's not. It's a college theorem. Yeah.
Oh.
I think this is called sometimes the fundamental theorem of symmetric polynomials.
Gotcha.
We have fundamental theorem of arithmetic, fundamental theorem of algebra. I think this is called, I'm not so sure of the terminology, but I have heard it being used. Fundamental theorem of symmetric polynomials. Yeah, and we do use it in high school when we, in the examples that I showed. Okay, so, and the problem is the following. So we know that monomials in these E1 through En do form a vector space basis, but there is a slight issue here, and that is the following. So let us look at the C x1 through xn, and there x1, x2, xn have all degree 1, right? So x1 square has degree 2, x1, x2 also has degree 2, and this symmetric the space of symmetric polynomials, you can think of it as a graded subring of this. So each element here has a grading, or not each element, each homogeneous element. There are, there is a, let me just say that there is a grading on this bigger polynomial ring, which is inherited by the smaller polynomial ring. But then En, if you think of En and suppose n is 3, E3 is x, and the variables are x1, x2, x3, En is E3 is x1, x2, x3, the product, which has degree 3. So the difference here is that E1 has degree 1, E2 has degree 2, E3 has degree 3, and so on. En has degree n. So the monomials in the EIs do not have, we cannot treat them as monomials of degree, as these E1 through En, although they are variables of different degrees. E1 has degree 1, E2 has degree 2, and En has degree n. So this makes it a slightly more involved, just a bit more involved. We just need to keep track of this to write a basis. So in the next few slides, I will illustrate this, but the theorem that we are, or the observation that we are going towards is the following. Suppose I want to, what is a parametrizing? What is a parametrizing set for all the monomials here in this symmetric, in the E1 through En, which form a basis for this ring of symmetric polynomials. The partitions form a natural parameterizing set. So if I'm looking at those of degree D, those of a basis for degree D piece of this ring, then, or this vector space, then partitions of D is the right thing to look at. We'll make this more precise in the next few slides. This is also very elementary. This we are doing again just college algebra. Okay, so the next, I'll go through the few slides maybe a little quickly, but this is all, I have already said what we are moving towards. So degree E1 is 1, degree E2 is 2, degree En is n. Okay, so the monomials form a basis. We have seen that. But if I take this monomial with M1, E1 to the M1, En to the M1, it has degree 1 times M1 plus 2 times M2 plus n times Mn, because this En has degree n, and En minus 1 has degree n minus 1, and so on. Okay, so let's think. Okay, so I hope you know about partitions. So for example, if I write this here, 5 plus 3 plus 2 plus 2, that is called a partition of 12, because if I add these numbers, then I get 12. And so here, this is a pictorial representation of that partition. It's called a Young diagram. So there are 5 boxes on the top row, 3 on the next row, 2 on the next row, 2 on the next row. I will not formally define, it's intuitively clear, but I think of this partition as E1 square, E2, E4 square. And why do I do that? Let me tell you how this bijection, this is a bijective correspondence goes. E1 square refers to there are two columns with a single box. E2 refers to that there is the number of columns with 2 boxes is 1. So the subscripts refer to the number of boxes in the column, and the exponents refer to how many there are. So E4 square refers to there are 2 columns with 4 boxes each. Okay, and if I do this bijection, then if you can see that E1 square plus times E2 times E4 square, if I think of this in terms of this partition, and then just count the number of boxes, which is 12, I get, it gives me 12, which is the degree of this monomial. So I will quickly go to the statement. A parameterizing set for the homogeneous piece of D degree polynomials is symmetric D degree polynomials in n variables with complex coefficients. This is a vector space subspace of this lambda n. It consists of partitions of D, all pictures like this with 12 boxes, but with at most n parts. This is the number of n parts, because there is only En. There is no En plus 1. So you cannot have a column with n plus 1 or more boxes. So that's the restriction here. So we get this theorem. So this is a nice way of parameterizing a basis for. So I do this illustration now. So suppose we have 4 variables, right? Sorry, 3 variables. Sorry, I made a mistake. 3 variables and degree 4. Let's see what the parameterizing set is. I must write all partitions of 4 with at most 3 parts, right? And I've written them here. And there is one more that does not count because it has 4 parts, but I'm allowed only maximum 3 parts. Okay, so and these correspond to the monomials E1 to the 4, E1 square, E2, E2 square, and E1 E cubed. Sorry, E1 E3, and therefore we can conclude that this vector space has dimension 4. Okay, and I make this comment. that this partition would also count if the number of variables was bigger than or equal to 4, then the vector space omega n 4 would have dimension 5, because this would also count provided n is bigger than or equal to 4. I hope this is clear. Let me pause here and ask if there are any questions. I'll be happy to answer. So what we have done is we have identified a basis for the for the vector space of symmetric polynomials. I'll just say basis for symmetric polynomials. Okay, and those consist of monomials in the elementary symmetric polynomials, and a good way of parameterizing them. If I want to look at degree d piece, then it's partitions of d with at most n parts, where n is the number of variables. That is the answer. And this is a very elementary fact, college algebra fact. Okay, so I presume that this is all right, and then move on. Okay. Okay, that's what we already talked about. Okay, the next thing we are going to do is what I promised. One of the things I promised at the beginning. I am now going to define Schur polynomials. Now I want to repeat something that I already mentioned, namely that this definition. I'll give you two definitions, and both of them are interesting. I will not tell you why these two are equivalent. Okay, that is not so easy to prove. Why these two are equivalent. Many things about facts will not be so obvious, but you have to take me at face value. But I will give you two different definitions of the Schur polynomials. Both of them are the same, and I repeat, it's not easy to see that both of them give you the same answer. So let us move towards that, and that is one of the important takeaways from this talk, if you have not already seen those definitions. Okay, let's so first is a combinatorial definition. In order to do this, I have to define one combinatorial gadget or object called semi-standard Young tableau. Okay, so towards that, so I have this is the notation for a partition of D. Let lambda be a partition of D. I think in the previous talk, Nitin was using this as a logical sequence or something, but here it means a partition. So let's do an example, the same example. Suppose I have 12, that is degree is 12, right? And I have this partition, and I take, so I fix a D, I fix 12, I fix a partition, which is, I fix this partition, and I also fix an n, which represents the number of variables. Okay. Okay. Now what I do is I fill the boxes of this partition with the numbers 1, 2, 3 up to n. So in this case, 1, 2, 3 up to 5. Okay. And repetitions are allowed. Not every element 1, 2, 3, 4, 5 need be used. Although in this example we have used all of them. But you could possibly not use all of them. That's also possible. For example, the second column would have been 1, 2, 3, 4, and not 1, 2. Also be a valid example. This keeps going down. I'm sorry about that. Let me just here is a list of all conditions. Entries along each row must be weakly increasing, and entries along each column must be strictly increasing. Okay, so this is just so I hope this is clear now. So what I do is I write, so I'm trying to, so let me go step back one second and remind you what we are trying to do. We are trying to define the Schur polynomial, and these are going to be a basis for symmetric polynomials. So it makes sense for them to be indexed by partitions. What kind of partitions? So if I fix a D, let's fix a degree. I'm looking at symmetric polynomials of a fixed degree, D. I fix, and with n variables, so the n is also there, d and n are the two inputs. And then so for each partition of d with at most n parts, I must produce for you a polynomial. And I'm giving you the recipe for producing it. What you do is you write the partition in terms of its diagram and start filling in numbers, right? And these are the conditions that you should follow. You should only use 1, 2, 3, 4, 5. Repetitions are allowed. Not everything need be used. Entries along each row must be weakly increasing. This means, for example, I have 1 here and then there's 1. In the first row, there is 1, 1, 2, 2. So that's okay. It's weakly increasing, but not strictly increasing. But the columns must be strictly increasing. So this looks very strange, and it's not clear at all what this has to do with anything that we have talked about. But you see, that's inexplicably, this has everything to do with symmetric polynomials. And what you do is you keep writing all of these tableau, semi-standard Young tableau of this given shape. There are many other ways of filling this with such that these properties hold. For example, I gave you another one where the second column is 1, 2, 3, 4 instead of 1, 2, 3, 4, 5, right? 1, 2, 4, 5. 1, 2, 3, 4 instead of 1, 2, 4, 5. That would also satisfy all these properties. Then what do you do? So to each filling, you can clearly associate a monomial, namely, to this filling, I associate x1 square, right? Why x1 square? Because there are 2 1s. x2 to the 4, because there are 4 2s. x3 cubed, because there are 3 3s. x4 square, because there are 2 4s, and x5. So the monomial I associate with this is x1 square times x2 to the 4 times x3 cubed times x4 square times x to the 5. Okay. What I do then is I have listed all the semi-standard Young tableau of this shape and with these conditions with d and n fixed. Then I have associated to each of them a monomial, and what I do is I take the sum of all those monomials, and that is the Schur polynomial. I hope I have given you the definition. I'll give you the illustration in the next slide. Okay, so here is a simple example. If you want to do a example of this size, for this partition, if I have to write the Schur polynomial, it is going to be very large, and it won't fit in one slide at all. It may require several slides. But here is a simple example. Simpler example for which we can write down, sorry, let me make this. Yes. This is what I wanted to illustrate. This is the illustration I wanted to give this is an example of a Schur polynomial. So what are my d and n here? D is 3, n is 3, and lambda is 2 plus 1. So I write this shape and fill it up with numbers 1, 2, 3 only, right? 1, 2, 3. I'm allowed to use, for example, if you look at this last one here, I have not used 1 at all, but that's okay. And repetitions are allowed. So 2 times 3, that is okay. And the conditions are, along every row, I must be weakly increasing, and along every column, I must be strictly increasing. And it's an easy check that these possibilities exhaust all the semi-standard Young tableau. And then I write out the polynomial as I described. So let's go through this. x1 square x2 because of this polynomial, this shape here, x1 square x3 because of this shape, this filling here, x1 x2 square because of the third tableau or filling, and 2x1 x2 x3 because there are 2 tableau which use 1 1s, 2 1s, and 3 1s, right? So you see the 4th and the 5th both give you x1, x2, x3, and since there are 2 of them, I get a coefficient 2 in front, right? And so this is the Schur polynomial, and it's a miracle that it is symmetric. Okay, so I have said, note that S lambda is symmetric in x1, x2, x3. That is easy to check in this given example, but in general, it is not at all clear why it should produce this recipe a symmetric polynomial. But I am not proving this, and this is a theorem which is maybe 20th century. This is not, I don't think this was known to Newton. So the S lambda are symmetric in the variables x1 through xn, it should be, sorry for this m, that's a typo. Moreover, as lambda varies over partitions of D with at most n parts, the S lambda form a basis for this vector space, which is D degree polynomials, symmetric polynomials in n variables. Okay, let me pause here and ask if this is clear, and I'm willing to answer questions. So, Professor Katra, should I continue?
No, Surya is asking something.
Oh, sure. Please.
Yeah, right. Sure.
No, I didn't ask anything. Sorry.
He's punning. Surya is in his elements.
Oh, I see. I'm missing it all. So I'll look at the chat box later. Yeah.
Yeah. Okay.
Yeah. I just said it's a young theorem.
Yeah. It's a young. Oh, nice. Oh, yes, it's a young theorem. Yes. Thanks, Suri. Yeah.
Suri, you missed my comment. I said sure.
Yes, sure. It's a young theorem. Right. There you go. We can. Yeah. I didn't notice either pun. I mean, thanks to Suri and Raghuram for those. Yeah. Okay. So keep the puns coming. Yeah. So the next slide, let me just show you the entire slide. So this is just, I've written down, if you work through this, you will see that the symmetric polynomials corresponding to these shapes in 3 variables will be these ones. Okay. Well, maybe that's not so. Okay, let me just quickly tell you the last one. Maybe not. Maybe it's okay. Let's go on. This is just an illustration. So let's just go on. Okay. So I'll give you an alternative definition of Schur polynomial. I promised I'd give you 2 definitions. Here is an alternate one. So let me just go to the end of the slide. Yeah. Okay. So I have taken this simple illustration here. Suppose my lambda is 2 plus 0 plus 0. Okay. The reason why I put this 0 plus 0 is because if I have 3 variables, lambda can have at most 3 parts, right? So I'm writing it as the second part is 0 and the third part is 0, and that is important for this this recipe for finding the Schur polynomial, this formula for the Schur polynomial. So what is this recipe? So if you follow the previous recipe, then you will get the complete symmetric polynomial here, right? In 3 variables of degree 2. Okay. So this is just the sum of all monomials of, if you don't know the definition, here is the definition. Complete symmetric polynomial of any given degree is just the sum of all monomials of that degree. Okay, easy definition. So for degree 2 in 3 variables, there are these 6 monomials and it is their sum. Okay. Okay, and here is another definition, another way of writing the Schur polynomial. Okay, and I do this in the illustration, but it is clear from this illustration how to generalize. Suppose I have lambda is equal to 5 plus 3 plus 2, for example. It is easy to make the change, and this is how you do it. So this, you see, the first column has only x1s, so it's a determinant by determinant. And I'm going through the columns of the top determinant. First column has only x1s, the second column has only x2s, the third column has only x3s, right? And what are these coefficients here? The 2, 0, 0 come from the partition, right? And that's why I put this 0, 0 extra, because there are as many rows and as many columns as there are variables. And therefore, if lambda, if there are empty parts in lambda, I just put zeros there. So I can fill this. So 200 is for lambda. And what is this 210? This is just something you add on. 210, 210, 210. If we were in the 4 variable case, n equal to 4, then it would be 3, 2, 1, 0. 3 you would add in the first row, 2 in the second row, 1 in the third row, and 0 in the fourth row, and so on. So I hope it's clear where these exponents are coming from. 200, 200, 200. The exponents are the same across the columns. What is the difference between the columns? The first column has x1, the second column is x2, the third column is x3. And the bottom is just this x1, is this what's called the Van der Monde determinant, right? So it's 1, 1, 1, x1, x2, x3, x1 square, x2 square, x3 square, right? And as we know, the Van der Monde determinant, if you flip any two of these variables by the property of determinants, we know it's antisymmetric. So the top is an antisymmetric polynomial, the bottom is an antisymmetric polynomial, and therefore this quotient is symmetric. So I'm giving you a proof, college proof, that what we are writing here is a symmetric polynomial, right? And also, why is this a polynomial? As you may know, this Van der Monde is just x1 minus x2, x2 minus x3, and so on, right? This has x1 minus x2, x2 minus x3, x1 minus x2. Sorry, x1 minus x2, x1 minus x3, x2 minus x3. It's a degree 3 polynomial. You take all differences and take product, right? And that divides this numerator, because when I flip x1 and x2, or if I substitute x2 equal to x1, then this determinant clearly becomes 0. Similarly, if I put x3 equal to x2, that shows that this is divisible by x3 minus x2. It's also divisible by x1 minus x2, also by x1 minus x3. Therefore, this quotient, although also I've written it as a quotient of polynomials, it's actually an honest to goodness polynomial, and it is symmetric. And so this is another definition of the Schur polynomial. And this, for those of you who may have seen a little bit of Lie algebras, semi-simple Lie algebras, this is just the Weil character formula. So if you look up the Weil character formula that appears in those courses, then this will not be the form in which it is given usually, but it is equivalent to that. Okay, so we've given two definitions of Schur polynomials. Now we'll come to the point of the talk, which is I take two of these polynomials, Schur polynomials, I multiply them, and try to write it as a sum of Schur polynomials. Then how do I do this? I will illustrate this in a very simple example. And you have to take it at face value, my statement that this is important, these coefficients are important in various fields of mathematics. So again, very inexplicably so, perhaps. They're important in representation theory, they are important in geometry, and in many other places. So let us, I will, very quickly go through this slide, which requires some college algebra background. Okay, so the background here is, you probably have studied characters of finite groups. Here we are talking about characters of Lie algebra representations, specifically this SLNC representations. So let me just compare the two here. For a finite group, as you know, the character is defined as a trace, and they are class functions, and they form an orthonormal basis for class functions. And very surprisingly, they determine representations. That is why we study them. Because although by definition they are only the trace of the matrix, somehow the matrices themselves are determined by the trace values, surprisingly. And pretty much the same thing holds here. So you can, while I have given you two definitions of the Schur polynomial, another definition would be as a trace. I mean, you may wonder how trace of what, etc. But I'm not going into this, but this is also a very well-known definition of Schur polynomial. You can, it's also realizable as a trace of, trace of a matrix. And they are symmetric polynomials. So instead of class functions, we have symmetric polynomials. And the Schur polynomials, for example, form a basis for, instead of class functions, we have the symmetric polynomials for the space of symmetric polynomials. And they are even orthogonal in a particular sense, which I will not go into here. And they also determine representations. So I thought I would point this out because the salient features of the finite group theory, which many college student, master students may be familiar with, are also true in the in the context of Lie algebra, semi-simple Lie algebra representations. Okay, now let's quickly go through this illustration. I will just illustrate this multiplication, which is the subject of my talk, in this very simple example. Okay, so let us just take two Schur polynomials. So which means I have to take two partitions, right? I've taken my number of variables is 3, and I've taken two partitions. One of them is this 2 plus 1. The other one is a single box, just the partition of 1. Okay. Suppose I multiply this polynomial with this polynomial. Both these are symmetric, and the product is going to be symmetric. And I express it as symmetric polynomials of what I get is a symmetric polynomial of degree 4. I try to express that as a linear combination of Schur polynomials of degree 4, which means I must write this times this is equal to some partition of 4 with some coefficient in front, some other partition of 4 with some coefficient in front, etc. What partitions do I see? The description is very simple. Let me just describe it. So what you try to do is you try to fit this box into this partition. You try to add this box to this partition. See, I want to get the sort of heuristic being, I want to get a partition of 4, right? How am I going to get it? I'm trying to just add a box, add this box so as to make this into a partition. So where all can I add it? I can add it here. I can add it to the first row. I can add it to the second row. I can add it to the third row, right? Okay. So so here is the answer. So it is the sum of these three. So when I take these two and multiply them, so that's given in the bottom. So this is the Schur polynomial S2 plus 1 times S1. That's equal to S3 plus 1, S2 plus 2, and S2 plus 1 plus 1. So there are no coefficients in front. I mean, all the coefficients of 1, okay, in this case. So that's a very simple illustration. And there is a rule which is called the Littlewood-Richardson rule. And as I mentioned at the beginning, it is more complicated. And let me not go into that. Let me see if I have another illustration here. I do have this illustration here, but let me just go to the final 2 slides because I'm out of time. So this requires maybe university mathematics. So let me give the representation theoretic interpretation and a few words about how this relates to some recent contemporary research, and then finally finish. So representation theoretically, so this V lambda and mu are partitions now. This V lambda is, with these partitions, you can also associate irreducible representations of the special linear group. So V lambda is one such representation, V mu is one such representation, and it is well known that you can take tensor product and the category of representations is semi-simple. In other words, any representation can be written as a direct sum of irreducible representations. And we have the statement that partitions also parameterize representations. So I can write an equation like this, right? And these coefficients in front are very important, as you can see, if you want to understand representations. And the point is, since characters determine representations, I can take the character of this, which is just the Schur polynomial corresponding to lambda. I can take the character of the second one, which is just a Schur polynomial corresponding to mu. So tensor product just means multiplying their characters. So the character of the tensor product is the product of the characters. So I take the Schur polynomial S lambda, I take the Schur polynomial S mu, multiply them, and express it as a sum of Schur polynomials. So the basic, very high school problem of writing the product of Schur polynomials as a sum of, as a linear combination of Schur polynomials has this meaning for representation theory, which is far-reaching. Okay, and the research work has to do with a certain refinement of this. So you have certain filtration of this called the Constant-Kumar filtration, consisting of the Constant-Kumar submodules. There are also modules for the Lie algebra. And so the question is about how those decompose. And so what you get on the right-hand side is this C, lambda, mu, nu, which are the LR coefficients, adorned with one more symbol, which tells you the parameter for the symbol, parameter for the filtration, the Constant-Kumar filtration, which happens to be just the while group. Okay. It's a little more complicated, but you can take it to be the while group. So in the SLN case, it is just, so you have C, lambda, mu, nu, and in addition, you will have a permutation of M. Okay. Okay, and this is my last slide. So I've already said this, the Lie algebraic LR rule contains the LR rule for symmetric functions as a special case. And as I said at the beginning of the talk, while I think of these LR rule, Lie algebra LR rule pretty much in terms of the symmetric functions. And there are generalizations of Schur polynomials called Schubert polynomials, and it's an open problem. What we have just done for Schur polynomials, a similar problem is true for Schubert polynomials. Similar problem exists for Schubert polynomials. They also form a basis for a ring. And therefore, the question is, if I multiply two Schubert polynomials and try to express them as a sum of Schubert polynomials, what are the coefficients? That problem is pretty much open, and it's a very famous open problem. So solving this would be very important. Would be anybody who solves it would become become famous. It's called the Schubert calculus problem, if you want to look it up. Thank you for your attention. Sorry for going over time.
Yeah, thank you, Professor Raghavan. Very nice talk.
Yeah.
Excellent presentation. So if you have anything, comments or questions, then you are most welcome. The participants, those who have come, most welcome to give any comments, feedback. There is some people want the.
So how do you? I'm happy to share the slides. No problem at all. I can send them to you.
You can send to me, and I will send to the participants whom I have invited. And some people have invited others, so to them they should send, because I don't know, may not have their email addresses. So at least I will send to those whom
no
I
problem.
send invitation.
No problem. I'm happy to send those slides to you.
Yes.
You could just put it on Bhaskaracharya Pratishtan's website.
That is also possible, that we can put on the website of the Bhaskaracharya Pratishthan. People can take from there.
Yeah, that's easier. That's easier. And I'll send you the slides. Feel free to put them on the website. I have no issue.
Thank you very much for that.
No problem.
Any other comments or something? If you want, you are free to do so. Yeah. And
Raghavan, thank you for a nice talk.
Yeah, Sudhir, sorry, you have heard this talk before. So
No, it's okay. It's always good to. So I mean, it didn't complete. So what is there a bearing on the platinum problem of your new theorem?
No.
Okay.
No. If there is, I don't know about it. No. Not in any way I can think of. No.
Mm-hmm.
There was the request that we should upload the recording also. So what we are trying to do is we are trying to put the recording on the YouTube channel. And once I get the link of that one, I will send that also, or I will put it on the Bhaskaracharya Pratishthan website or send to the participants. That is one thing. Another thing is that just now I got a call from the house of Professor Abhyankar, Sridhar Abhyankar. And I was told that because there was some failure of hearing for that presentation of Sridhar Abhyankar, so because of that, they also are trying to put it on the YouTube. So if I get that link, I will share it with you today itself. Probably we'll get it by the end of the next talk. That is what we expect. So maybe Yeah. Any other comments anybody wants to make? Most welcome. Otherwise, we'll have a break of 5 minutes because it is continuous thing. So 5 or 10 minutes. What is your suggestion? And then we will have the next lecture. So
You could start at 5:45. So 6 or 7 minutes.
So in between, I'll just make some presentation about Pratishthan. People may see or may not see. That's different. So 5:45 we will start lecture.
Make a suggestion.
Yeah.
Somehow I don't see any link about this symposium on the webpage of Pratishthan. I don't know why. I mean, there are several events mentioned there, but
no, we do not put because I know only 100 people I can accommodate at a time, and today many people could not attend. Many people are calling me that we cannot enter. So there was a number 101. After that, those who tried after that, they couldn't attend. Therefore, I had not deliberately I didn't put it on the website because today there was a problem for Raghavan also, Ken Raghavan. What happened? He was almost the last person. He entered and immediately was thrown out, and fortunately he was able to enter. That was the problem. And Sridhar Abhyankar could not enter, for example, because he was more than 101 number. So that's why I did not announce it. Deliberately I did that because there are other ways of doing it. There are 256 participants also possible, but that I have not tried, means I didn't get time for that one. So that is the reason actually. But next time we will do a better job.
Correct. And any of the previous symposiums, I mean, ideally one should have a record of all this. You know, you have now been doing it for a few years. And see any web page. Hello.
Yeah, the previous symposia are with Pratishthan. So we should do it, put it on YouTube or something like that because the size is very large. So we have not put it on the YouTube earlier because but we should do it if possible. Yeah, we will try for that. But this is certainly possible. It can be put on the YouTube, and we are doing recording. Yes.
Okay. Thank you.
Yeah.
So Katre, are you going to say something? Or should I try sharing my slides?
No, showing some slide, but you don't have to see that. It is just It is up to Professor Abhyankar and so on. We already heard of it, but
no, I'm happy to hear.
And so on. Yeah, so this is childhood of Abhyankar. He was born in Ujjain, Madhya Pradesh.
Okay, I'm not able to see the slides you're sharing. Are others able to see the slides you're sharing?
Yeah, I don't see anything. I see.
Can you? You are not.
Katre, you want to do some sharing of your.
Once more. Maybe I think I have not done it properly. So let me do it again. I have to present. Share. I think I forgot to do sharing of that one. Yeah. Now I think I should be able to do it. So yes, right. Thank you. So now I think you are now it. So this is the photograph of Abhyankar and usual photograph. Childhood of Professor Abhyankar. He was born in Ujjain. And once there is a story that once his father locked up his mathematics books, so he got off very early, and with the help of his uncle, he got that whole treasure. That was his idea.
Can make it full screen. We can barely read what.
I see. Okay. Yes. This I think you can. 1 minute.
Okay. Better.
Yeah. Slide. Slide show is possible. Yeah, right, like that. These people can big one.
Sir, make it slideshow, sir. Slideshow.
Essentially, it is slideshow. You can see, no?
It is not a slideshow. If we full screen, yeah,
No,
now it's,
no.
it is full
That's
screen.
fine.
Yeah.
That's fine. That's fine.
Yeah. Abhyankar earned his BSc from Royal Institute of Science of University of Mumbai in 1951 and AM at Harvard University 1952, PhD Harvard 1955. Thesis was written with Professor Oscar Zariski, local evaluation of algebraic surfaces over modular ground fields. So before Purdue, he was associate professor of mathematics at Cornell University and Johns Hopkins University. He was appointed Marshall Distinguished Professor of Mathematics at Purdue in 1967. Various topics he worked on: algebraic geometry, commutative algebra, local algebra, valuation theory, theory of functions of several complex variables, dynamics, circuit theory, invariant theory, combinatorics, computer-aided geometric design, robotics, and he popularized the topic Jacobian conjecture. So Abhyankar's work can be divided in fairly distinct phases, during which he focused mainly on one broad topic and made substantive contributions. He has about 200 research papers and author of about a dozen books. His most recent one, as I see, is Algebra 1, which is a very thick book. He wanted to write Algebra 2 also, but that was not possible. Various honors and awards received by Abhyankar. Okay, now what Pratishthan, it was founded by Professor Abhyankar in 1976. His aim was to conduct research in higher mathematics. Right now, Pratishthan is organizing mathematics Olympiad activities, also various activities for undergraduate students. There are a few postdoctoral fellows at the Bhaskaracharya. The Bhaskaracharya Pratishthan gets some support from National Board for Higher Mathematics for its activities and library. The teachers from various colleges in Pune, ISER, SPPU, Pune University, and various institutes all over India like TIFR, IMSC, CMI, HRI, IITs, ISI, and many researchers from these institutes, they are helping the activities at the Bhaskaracharya Pratishthan. The Pratishthan supports a few postdoctoral fellows for research in higher mathematics. Some of the lectures are online now. Even at the high school level, there are some lectures at the in the online form. There are some mathematicians associated with the Bhaskaracharya Pratishthan: Professor Bhatodekar, Ravi Kulkarni, then Dinesh Thakur, Kaushal Verma, Nitin Nitsure, Mangala Naralikar, Solapurkar, Acharya, and some of the previous governing body members, Simha, Balwant Singh, Rajendra, helped the activities in the Pratishthan in many ways. And there are some staff members at the high school level, college level, and Olympiad level. Some of the names I have mentioned here, they are all helping in the high school and undergraduate and postgraduate activities of Bhaskaracharya Pratishthan. And this is the abstract already the lecture of Nitin Dussare is over, and the second one is Abhyankar, and this also is over now. Already I had sent these abstracts to people. And this is the next one. Yes. Okay. So I will now stop sharing. Already.
So I should start sharing mine.
Yes, please. So I'm stopping now. Yes, so now I invite Professor A. Raghuram to give his lecture. Professor Raghuram, he is the first head of mathematics at IISER Pune. And again, the Bhaskaracharya Pratishthan and IISER Pune, they have an MOU. So we are helping each other. And academically, I think IISER is helping Pratishthan more because of very distinguished staff members at the IISER. So I thank IISER for that. Yes. So Professor Raghuram is talking on an interesting topic, the usefulness of useless knowledge or mathematics. So both the things are there, I think. So I invite Professor Raghuram to start his talk.
Okay, thank you, Professor Katre. Can you see the slides?
Yes, please. Yes, certainly. We can see the slides.
And is it full screen? Is it full screen or is it like a little box?
No, it's full screen.
Okay, sorry. Okay. So, so thanks a lot to Professor Katre and to Bhaskaracharya Pratishthan for asking me to give a talk in this Abhyankar symposium. Maybe I should share, or almost contact, I should say, I've had with Professor Abhyankar. So sometime, when was this? I spent a semester, I think it was spring semester of 2003 as a visiting assistant professor at Purdue University. And you know, if you've been to Purdue, you know that there's this coffee room inside the library, in the library floor, and every afternoon at 3 or 3:30 there is coffee and cookies, and I would go there sort of diligently every day to kind of meet people and you know, spend some time. And Abhyankar would be there, and somehow the entire semester I never could muster my courage to go talk to him. Although almost every single time I was there, he would kind of check me out, you know, who is this? Someone clearly from India. And I kept thinking that, okay, I should talk to him, but I don't know, he just felt and looked so intimidating that I feel like an idiot now that I should have, that I didn't get a chance to talk to him, talk mathematics with him. So he was, so that's that. So as far as this symposium and the talks you have heard so far, you know, Nitin's talk about logic, and it was sort of very philosophical. And Raghavan's talk was, it's about this beauty of these symmetric polynomials and Schur polynomials, and how over the last century there's been this very beautiful theory over there. So my talk, maybe you should take it in the spirit of this is like just the culture of mathematics. So this title, the usefulness of, you know, this is a title which is borrowed. You will see this in my abstract. It is borrowed by this famous, the title of a very famous essay of Abraham Flexner. Now, this is the very first page of Flexner's essay, which appeared in the Harper's Magazine in 1939. So let me see if I can zoom a little to in. Do you people see the zoomed version now?
Yes, yes.
Okay, very good, thanks. So, by the way, please, before I go any further, please feel free to interrupt me anytime, because, you know, as Raghavan mentioned, this is one of the biggest challenges, I think, facing all of us faculty at various places. We are all into now this online teaching mode, and the biggest problem, I think, is the lack of real-time feedback. So I'm looking at my slides and I'm talking into a screen and I have no idea if it is reaching across. So please interrupt me anytime and ask me questions. Okay. Okay, so this title, The Usefulness of Useless Knowledge, is this article by Flexner. And let me just read out the first sentence in this essay. He says, "Is it not a curious fact that in a world steeped in irrational hatreds which threaten civilization itself?" Okay, you got to remember, this is 1939. Okay, so Second World War is just broken out, and America and much of the other world has passed through this Great Depression. So it was not good times, if you think of that. So is it not a curious fact that in a world steeped in irrational hatreds which threaten civilization itself, men and women, old and young, detach themselves wholly or partly from the angry current of daily life to devote themselves to the cultivation of beauty, to the extension of knowledge, to the cure of disease, to the amelioration of suffering, just as though fanatics were not simultaneously engaged in spreading pain, ugliness, and suffering. That kind of sets the tone for this article. You should, I strongly encourage you to just Google the usefulness of useless knowledge, and you will see the facsimile of this article as it appeared in Harper's on the website of the Institute for Advanced. I will tell you a little bit about Flexner in a moment. So you see the years when Flexner was around, and he was the founding director of this Institute for Advanced Study at Princeton. This is a photograph again from the IAS archives. You see this person on the left extreme, which you can recognize by his hairstyle, and this is Flexner. I don't know who these two people on the right are, and this is in front of the Fuld Hall at the Institute. So Flexner was the founding director at the Institute, and he played a very major role in medical and higher education in North America. He himself, I think, had a bit of medical background. He was at Johns Hopkins, which was one of the pioneering research university at that time. It was probably one of the best schools in medicine. And there is I think there's a Flexner report early last century, which somehow reformed a lot of medical education. And this essay of his had a huge role to play in the evolution of the Institute for Advanced Study. So, yeah, if you for his life and works, you could go to this website of the Institute. I will be happy to share the slides with Katre, and then he could put it up somewhere. If I will be offering many such websites and references as, and you can, if it piques your curiosity, you can go take a look. Yeah. So here are some quotes from Flexner's essay, which somehow also set the tone for my own talk. So he says, throughout the whole history of science, most of the really great discoveries which had ultimately proved to be beneficial to mankind had been made by men and women who were not driven by the desire to be useful, but merely the desire to satisfy their curiosity. And he goes on, institutions of higher learning should be devoted to the cultivation of curiosity. And he offers a whole lot of examples. It's a very well-written essay. You could also read this essay to appreciate how to structure an article and appreciate aspects of the English language in this essay. Anyway, so he offers a lot of examples, and he goes on to say that in the domain of higher mathematics, almost innumerable instances can be cited. I'm not for a moment suggesting that everything that goes on in laboratories will ultimately turn to be of some unexpected use. But rather, I'm pleading for the abolition of the word use and for the freeing of the human spirit. So somehow, to ask what is useful is simply maybe not the right question to ask. The word use itself there's a bit of a problem. And as far as knowledge is concerned, you just cultivate curiosity is somehow the vision of that institute and maybe many other places. So in this talk, what I want to do, so going back to, as Flexner gave some examples, and I want to present a few examples from the domain of higher mathematics of real-world applications, which were possible only because someone had developed ideas entirely to satisfy their own curiosities. Of course, the moment I say that, many of us, all of us probably have our own favorite examples. What follows are a few examples that appeal to me at this point of time. 10 years ago, something else might have appealed to me, and 10 years later, if I'm alive and working, possibly some other examples might appeal to me. So I picked one example each from drawing ultimately from the subjects of algebra, analysis, and topology. Okay. I also hope to make a case via such examples, and this is somehow my, I guess, the theme of this talk, that other than abolishing the word use, as Flexner suggests, we should also break down what I think is a totally artificial barrier between these adjectives of pure and applied as far as mathematics is concerned. Okay, so this is the thesis of my talk. Okay, so let me jump to my examples. So before I jump to the word Flexner or anything, or his essays, please feel free to interrupt me and ask. Okay. So my first example is robotics and computer vision. And whatever image that are flashing through your mind, the moment I say robotics, I wonder if what robotics and computer vision, robotics as practice now, this is an interesting story. So Sir William Rowan Hamilton was finest mathematician that Ireland has produced. He is was an Irish mathematician, physicist, astronomer. He held the post of Professor of Astronomy at this title of the Royal Astronomer of Ireland. Fancy as it sounds, there's an interesting story. I don't know the details of the story, but Hamilton never became Fellow of the Royal Society, which was in England. And apparently, the story is something like the Royal Society did approach him, but he, I think, said no because he couldn't afford it. It cost £4 per year or something like this, and the salary that was offered to the Professor of Astronomy at Trinity College didn't really give him that freedom of spending £4. Of course, we are talking, you see, we are talking 150 to 200 years ago. Anyway, Hamilton, I urge you to go read a biography of Hamilton. Try E.T. Bell. Very interesting life history. He was a bit of a child prodigy, and some mentor had this rather insane idea: child learn several languages. And I think by the time Hamilton was 12 or 13 years old, he knew about 12 or 13 languages. You might say that's kind of ridiculous education, but so be it. So luckily, Hamilton's inner drive for mathematics withstood that onslaught of learning languages. Anyway, in my talk, I want to touch upon probably Hamilton's, one of his most famous creations, namely quaternions. Now, the story of quaternions itself is pretty interesting. So let me just mention a few details. You see, Hamilton tried to generalize the notion of complex numbers. Now, all of you know what's a complex number. It looks like x plus iy, where x and y are real numbers, and I is the square root of -1. So it's really a pair of real numbers. So complex numbers is just R2. By the way, do people see my cursor on my slides if I did this?
Yes.
Could someone?
Yes.
Okay. Okay. Yeah. Thank you. And by the way, if there are comments in the chat, I will, since I have made my slides full screen, I won't be able to see the chat session real time, but after my talk, I can take a look. So anyway, so complex numbers is just 2 copies of real numbers. And then there are some standard rules that you're all familiar with. I don't know when we learn complex numbers, maybe 10th standard or 11th standard, or whenever you learn it. You know how to add, subtract, multiply, and divide complex numbers. Okay, so all that was known before Hamilton. Maybe Gauss. Anyway, so Hamilton worked very hard in trying to make R3 into a field. So, if I take 3 tuples of complex numbers on that system, can I somehow throw in some formulae where I can add, subtract, multiply, and divide, making it into a field, as we call it. And he worked very hard on this problem. It said that he worked almost 10 years continuously on this problem. And The story is the idea of quaternions occurred to him on a very particular date, the 16th of October, 1843, as he was walking over the Brougham Bridge in Dublin. So I actually Googled, I went to Google Maps to see if this bridge exists. And so now on Google Maps, it shows as Broom Bridge. So Broom and Brougham are, I don't know, I guess, phonetically pretty close. Anyway, in some places in literature, I've seen it as Brougham Bridge. So he realized that you can't quite do this for R3, but you can actually do this for R4. If I took 4 tuples of complex numbers, then you can actually add, subtract, multiply, and divide, except you got to give up on commutativity of multiplication. That is, if I change the order of multiplication, then you might get different quantities. And the very basic formula which we learn in our, I guess, undergraduate studies is this H is for Hamilton. Hamilton's quaternions is this 4 tuple of real numbers. So as a 4-dimensional vector space, I write it like R plus Ri plus Rj plus Rk. My basis elements are 1, I, j, and k. And the rules of multiplication, after you account for distribution of multiplication or addition, and after you account for the real numbers, commutes with everything by definition here, it's how does I multiply with itself and with other, the j and k. You can deduce all of that from these equations. I square, j square, k square are all -1, and so is ijk. Apparently, it's these formulae that this line here, which Hamilton got so excited when he had this flash of insight on that date, that he carved this into a stone in that culvert in the bridge. So I told you I went to Google Maps to look up this bridge, and okay, before I show you a picture of that bridge. So it's a trivial exercise from these. You just manipulate a little. You can show that ij is minus ji. So that's already telling you that I and j don't commute with each other. And there's some cyclic way in which you can remember this. I times j is k, j times k is I, and k times I is j, and ij is minus ji, and so on. So let me show you a picture of this bridge. So this is this bridge, the famous bridge where Hamilton had this insight of quaternions. Of course, this bridge could be anywhere. I guess I have walked at, on such bridges somewhere in the Midwestern USA. So it can be anywhere, literally. But that little plaque there, you see. So I have another photograph of that plaque, and what it says is, here, as he walked by on the 16th of October, 1843, Sir William Rowan Hamilton, in a flash of genius, discovered the fundamental formula for quaternion multiplication, and that's this I squared equals j squared equals k squared equals ijk equals -1, and cut it on a stone of this bridge. Okay, so this is a nice story. So what's quaternions got to do with robotics? So remember, that's my example, robotics and computer vision. So for this, there's a relation between quaternions and rotations in 3 space. So I would like to explain a little bit of mathematics as I go along. And please understand, these examples, there is no way with a storyline traversing, literally almost 2 centuries here, that I can offer enough details to, for an expert to appreciate. But it is, think of these examples as, I'm just opening a certain window, maybe whetting your appetites, and if you like it, you should start looking around. I think it's pretty exciting. So let me do a little bit of algebraic jugglery. So I take a quaternion, I'll call it xi, a plus bi plus cj plus dk, a, b, c, and d being real numbers, the I, j, k being those basis elements, and I define its conjugate almost exactly like you do with complex numbers. What is the complex conjugate of x plus iy? Well, it is x minus iy. Here, there are actually 3 copies of complex numbers. I can think of a plus bi as a complex number. I can think of a plus cj as another complex number, and a plus dk. So there are sort of 3 copies of complex numbers in H. Those of you familiar with algebra, there are, C is a maximal commutative subfield inside H, and sits in 3 ways. Anyway, so I define the conjugate of xi as a minus bi minus cj minus dk. And then if you use those rules of distributivity and I squared, j squared, k squared is -1, and ijk being -1, and kind of mess around a little, you will see that the norm of xi, if I define it as xi times xi bar, then this turns out to be a squared plus b squared plus c squared plus d squared. And in fact, it's a homomorphism from the group of non-zero complex, non-zero quaternions to positive reals. maybe let me just digress for a second here. So actually, the fact that this is a homomorphism, in it lies this slightly more ancient result, probably going back to Lagrange, that you see there's this very famous theorem in elementary number theory that every positive integer is a sum of 4 squares. And if you want to prove this theorem is due to Lagrange. It boils down to proving it for primes. And that is because a product of two quantities, which are the sum of 4 squares, is also a sum of 4 squares. And that just boils down here as if I take two quaternion xi and say something else, say psi, the norm of xi times psi will be norm xi times norm psi. And if you sort of unravel that, it will boil down to this. I think this particular detail really goes back to Euler, I think, if I remember correctly. Anyway, so I have a group homomorphism from non-zero quaternions to positive reals. And the kernel of this norm map is often denoted SL1H. It is just, it's like as if I'm looking at some kind of determinant. I'm taking, anyway, it's the kernel of this map. And topologically, so what is the kernel? So I'm looking at all those elements whose norm is 1. So a squared plus b squared plus c squared plus d squared equals 1. So I'm looking at all 4 tuples of real numbers of unit distance from the origin. So that's like the 3-sphere. Somewhat more generally, like the norm 1 elements inside complex plane is an S1, yeah, in R2. So this is like S3 in R4. I will just skip this unitary group. So I take such a norm 1 quaternion, and I take a vector in R3, but I think of this R3 as just the, so to speak, the purely imaginary parts of quaternions. That is, it lives in the Ri plus Rj plus Rk. And then if I conjugate this V by xi, I look at xi V xi inverse, then it's again a check. You can sit down and do it as an exercise. This also lives in the same space, the same R3. So what you get is you get a homomorphism. It's called the adjoint. That's why the add, going from this norm 1 element to SO3. Now, what is SO3? SO3 is the 3x3 matrices, orthogonal matrices of determinant 1. This is the rotation group. I take 3 space and I kind of rotate it. I look at all possible rotations. I can fix the z-axis, move the xy plane. I don't know if you can see me hand waving in my video. You can move the xy plane, or I can fix, say, whichever y-axis and move the xz plane. So all these rotations generate a certain group, and that is SO3. And this one is slightly bigger than SO3. And the punchline, which connects Hamilton quaternions and what you can do with quaternions with computational mathematics, is the idea that doing calculations with SO3 is, you can do this much faster if I translate that calculation to a problem with calculating with quaternions, norm 1 quaternions. And this simple idea involving quaternions goes into this $100 billion business. It's an industry with robotics, computer vision, and graphics programming, and what have you. So like I said, this talk is, think of this for the sake of culture. Of course, there is a huge leap of faith going on from, I have to talk, I should show you some particular calculation in SO3, which somehow is computationally faster in SL1H, and what sort of calculations are relevant. So instead of explaining that, I'll just show you just this paper. It's called Quaternions for Computer Vision and Robotics by Webb. This paper, it's called Quaternions for Computer Vision and Robotics by Webb, John Webb and Pervin. Webb is a computer scientist at, this appeared in the proceedings of some conference. So here is a random page in this paper of theirs. And let me try to zoom in a little to see if I can catch a sentence here. Yeah. So I have zoomed in on my computer. I hope you can see the version, and if not, please let me know. So
yeah, it is seen, yes.
Okay, very good. Thank you. So let me just stare at this sentence. So another field in which quaternions come in handy is the study of robot arm orientation. So traditionally, a robot arm is thought of as a series of links, each with its own coordinate system, blah, 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 blah. And then you're working with some matrix like this 3x3 matrix with all these terrible looking theta i's and alpha i's. This is a 3x orthogonal matrix probably it's a rotation, so it's of determinant 1. And there's a picture where the symbols are explained what this means. And this article is actually a very nicely written article. I had a pleasant time kind of browsing through this, where it is very mathematics friendly. You see, there's I think in Nitin's talk there was this thing of math and physics and this conversation between them. These conversations across subjects can be difficult because people just grew up in different traditions, and this paper is very mathematics friendly, even though it's written by computer scientists. And then if you had some basic algebra about quaternions in your system. So this first example is an example from algebra where quaternions and calculation with quaternions, how are so relevant in computational mathematics. Of course, if you think of some movie, I don't know, like Avengers or something, and there is all this real time, continuously changing all these graphics. Somewhere deep there is some quaternionic calculations. I just find this idea amazing. Those of you who know this, quaternion algebra is a special case of division algebras, and there is, I think, some school in California which is studying division algebras and their relevance in electrical engineering, and it's very interesting. Okay, so that was my first example of an algebraic nature. Here is my second example, having to do with tomography. So what is tomography? So tomography is a technique for displaying a representation of a cross-section through a human body or a solid object using X-rays or ultrasound. I think I just picked the sentence off the internet somewhere. Tomos is a Greek word standing for slice or section. And here's a picture. All of you have seen this kind of thing. If someone has a stroke, for example, and is taken to the hospital, and you want to know where the blood clot was, they do a brain scan like this. And actually, I used to be very active in sports, and I busted my knee a few times. And once I had a very serious ligament injury, and they did MRI. I don't have those things to show. So these kind of MRI scans, CAT scans, these are very, very common in the medical world. And I'm sure all of you have seen this, or at least on television. So what is this got to do with mathematics? So this goes back to this mathematician Johann Radon from 1887 to 1956. Here's Radon. He was a mathematician based in Vienna. And this is a plaque, I think, where he was born. So let me just stare at this a little. Here is something in German. In diesem Haus wurde am 16. Dezember 1887 der österreichische Mathematiker Johann Radon. So it says in this house was born on 16th December 1887 the Austrian mathematician Johann Radon, Rektor der Wiener Universität und Mitbegründer der Computertomographie geboren. So he was the rector of the University of Vienna, and he is the co-founder of computer tomography. That's and this photograph is interesting. I mean, he's just teaching some basic calculus here. He's actually telling you what's the definition of a limit, and is computing some easy limit as an exercise for the calculus students. So tomography has this. I'll just give away the punchline. It goes back to this paper written a little over 100 years ago by Radon. Berichte der Sächsischen Akademie der Wissenschaft. It just simply means reports of the Saxony Academy of Sciences, or something like that, of Science, Saxony Academy of Science, or maybe Saxonian Academy of Science. So Radon's paper, here is Radon's paper. Okay, I want to stare at this paper. This is, of course, an English translation of Radon's paper, which was published in one of the IEEE journals, 1986. This paper is just calculus in two variables, okay? So let me again zoom in a little to make you appreciate certain aspects of this. I somehow couldn't fit in everything that I wanted to in one slide. The zooming in trick occurred too late after I prepared my slides. Anyway, you see this, the section A of this the determination of a point function in the plane from its straight line integral values. So what's Radon doing? He takes a function little f. This is a function in this theorem 1. He takes a function little f, which is a function defined on R2, on two spaces, a function of two variables. And he takes a line G having a certain, written in a certain style. It's just a line in two space. And then he computes the integral of this line, integral of this function along the line. So this integral is set up with respect to variable s, and this is typical notation for the arc length. So I'm kind of integrating along it's a line integral, if you will. So the Radon transform, as people now call it, of this function little f is this functional capital F, which is different lines in two space. Okay. And then the point of this paper is, if I knew the integrals, okay, so you got to take this little f to be satisfying some suitable regularity conditions. Let's just say this is, I want to integrate, okay, so let's just say it's continuous and has compact support. So outside some closed bounded subset of R2, it's 0. Okay, take such a function. And you take these integrals along lines. So this package of information, which is denoted capital F, is the Radon transform. And what he does in this paper, he says that if you knew this package of information, the values, all these values of integrals, then you can reconstruct little f. So what he does is, so this is the inverse Radon transform going on, that the mean value, let's give you the essence without reading out everything. So you take a circle centered around the point P, you take a circle, take all the tangents, and take the value of this capital F that you know on all these tangents, and out of that he, cooks up this function as a function of this radius, and it's a bit of Cauchy integral like formula, and this theorem 3 is really the inverse Radon transform spelled out, which is unfortunately cut out here. So once I know a function, given a function, if I knew its averages along all lines, then I can reconstruct the function. Okay, this is pure calculus in two variables. Those of you who have taught calculus in two variables, you can go back to Radon's paper and explain this to your students. It's that elementary, so to speak. And I've already told you what the Radon transform is, and an integral transform that takes a function f in two variables to a function capital F defined on the set of lines in that xy plane, and the value of capital F on a line L is the integral of little f along L. And the inverse Radon transform reconstructs little f from capital F. And as Radon explains, this works in several variables. Okay, and now if you go back to this imaging, what's happening here? You have now a function of three variables, which is somehow packaging the information of this solid object, in this case the brain, some human brain. And one is looking at various slices. So one is doing, instead of a line in two space, what you're doing is you're taking hyperplanes, all kinds of hyperplanes in three space. Or you can take codimension 1 subspaces inside n space. And if I knew the average of a function on all these, along all these hyperplanes, then you can reconstruct the original, which has transformed, everything about imaging these. Founded ultimately on the simple idea of Radon calculus in two or more variables. I just find this very, very beautiful example. It's a good example to know, especially, I will come to this thing of, you're often drawn to conversation, casual settings. People want to know is this useful and so on. And this is a very good example to know. Everyone who's had at least 12th standard mathematics has seen differentiation and integration, even if they don't remember it 20 years later, but at least they've heard these kind of things. They've heard calculus, and you could try explaining this. There is a book which actually I was not able to lay my hands on thanks to this pandemic and lockdown, but I did see some aspects of this online. It's called the Radon Transform. It's the proceedings of a conference where they started with the paper of Radon and kept track of all aspects of human knowledge, medical imaging, what have you, that has come out of this paper. And this is a good volume to have in libraries, I think. Okay, so this example is an example coming from analysis and very, very relevant to medical science today. And the third example is a very exotic example, which I'm just beginning to understand a little bit of. Okay, I have to tell you, I'm not an expert on any of these examples. They are examples which appeal to me. I just wish I knew them to a deeper extent. This example, which I'm going to offer to you about data science, which is a sort of hot topic these days, somehow appeals to whatever I know in my worldview of mathematics. So anyway, so data science is this, like I said, is a hot topic. Everyone wants, IISER Pune is trying to build a department in data science. I read this somewhere on the internet. Did you know that 90% of human data that's there in the world now, 90% of it just 2 years, not 2 years ago, in the last 2 years. So just think 90% of data has come on in the last 2 years, which is to give you an idea of the rate at which data is exploding. And people want to know, how can you efficiently package data? You know, what kind of tools and techniques do you need to know for data analytics? And this storyline goes back to good old Euler. So one aspect of data science, and I would like to mention this example. Sorry about that. Yeah. So there's Euler. Actually, I've started many talks, kind of semi-popular talks, starting with the story of Euler having to do with summation 1 over n squared, which is one of my favorite theorems of Euler. Summation 1 over n squared being pi squared by 6. But this one is a different example. Euler arguably is the most prolific mathematician ever. And I want to talk about, or start this example by talking about Euler's formula, which is this very classical thing. Almost all of you have seen this: b minus e plus f equals 2. I put this in quotes, Euler's formula in quotes, because apparently there's a long history about this formula. So it seems it was known to Descartes. Euler proved this, or he thought he proved this. Apparently there was a flaw, and then, you know, there's almost 100 or more than 100-year history to from its starting point to its final, you know, for it to have been proved. Anyway, so let me just tell you, you know, at least for the sake of students who are just starting out, who might be listening to this talk. So what's Euler's formula? So if I take a polyhedron, so what is a polyhedron? It's a solid whose surface is a number of polygonal faces. Okay, so for example, you know, if you think of a football, the classical football, this is what's called a buckyball. You know, go Google this. Its surface is made out of hexagons and pentagons, I think. I will be showing you many pictures of polyhedra in a moment. So a polyhedron is said to be, it's kind of, I'm hand waving. If you can see me hand waving, there's no holes through it. It's not a word donut like thing. It's like a sphere almost. Topologically, it's a sphere. In a simple polyhedron, if V stands for the number of vertices, E the number of edges, and F the number of faces of the polygons on the surface, then Euler's formula says that V minus E plus F equals 2. Okay. A polyhedron is said to be regular if all the faces are congruent and all the angles that are meeting at a vertex, at any vertex, they're all equal. Now, all of you have seen these regular polyhedra. They're also called Platonic solids. This adjective, of course, coming from Plato. This was known to the Greeks, that it's an amazing fact of the world around us that there are exactly 5 of these regular polyhedra. This is just an aspect of geometry of just very, you know, pristine beauty. So that there are only 5 Platonic solids. The way I've listed tetrahedron, cube, what is this? Octahedron, icosahedron, and dodecahedron. And these, a proof of this, you can prove this using Euler's formula.